Okay, so we're getting ready for our keynote, but to introduce the keynote, we think it would be better to roll a video.
Okay.
Let's do it.
Yes. Kirk.
Jack, how are you?
Nice to see you.
Good to see you as well.
Well, I don't want to really read through all this stuff about you.
Please don't.
You're going to have to distinguish yourself by just talking. Ladies and
Perfect.
gentlemen, this is Kirk Johnson. He's the curator. He's one of the great scientists of the planet. And I've come to know you personally. I'm just going to shut up and let you talk because you'll distinguish yourself, believe me.
Thanks, Jack.
Thank you, Kirk.
Thanks,
Right,
Kurt.
how are you?
Thank you.
Hello, everyone. That kid in the film, that was me. I was 12 years old 52 years ago. And looking at my first dinosaur in the National History Museum in London. Already by that time, I was a big National Geographic fanatic. I was a fossil collector. And this is the first time I was in a big museum. I was pretty much lost after that. I really became a museum kid. It was an amazing thing. And now I run the Smithsonian's National Museum of Natural History, which is the world's largest natural history museum. I'll tell you a little bit about the Smithsonian first. It was based on a gift made by an Englishman named James Smithson in 1829, coincidentally the same year that the word scientist was first used. And the Smithson gift was dedicated towards creating an institution for the increase and diffusion of knowledge in the city of Washington. So you can see there the Smithsonian, the red brick building in the middle of the mall where the uncompleted Washington Monument is. And the Smithsonian was really our nation's first investment in science. So many of the major science agencies of the Smithsonian, or the nation, like NOAA and NASA and USGS, the Bureau of Technology, all have their roots actually in the Smithsonian. So it was the first time our country realized that we need science to run a country. Now, if you go to Washington today, the Smithsonian is 16 museums in the National Mall. And it's really a wonderful thing that our nation wraps itself in museums, places that are dedicated toward the increase and diffusion of knowledge and sharing it with people from around the world. What's so cool about the Smithsonian is that it is a lot like what GIS people do. It's the gathering of information, the analyzing of information, the sharing of information. So I find myself, when I talk to Jack Dangermond, in close agreement almost always. It's always how do we gather the information? How do we analyze it? How do we share it? And how do we share it with all the different audiences? I say also that, like, in the same way that GIS is more than just about maps, museums are more than just about exhibits for kids. They are places of knowledge creation and sharing. I have the privilege of running this museum. It was opened in 1910. It presently gets about 4.5 million visitors a year, which means, and most of them are American tourists. We're apolitical, nonpartisan, we welcome everyone. We see something like 4 million unique American tourists every year. That means in a decade, we see about 40 million different Americans. That's about 12% of the nation's population. So in our doors, it's an amazing way to communicate science. But also, behind the scenes, what most people don't realize is that we hold the world's largest collection of natural history objects. Rocks and minerals and fossils, plants, animals, insects, fish, birds, mammals, the entire core. And in a way, I would say that we are the analog twin of the natural world. You're used to digital twins being digital copies. We're the actual real visceral form copy of the natural world. 148 million objects. I often say that is like or very similar to infinity. It's a big number. I call us also the forever place because we hold these things forever on behalf of the nation's people. Or the Fort Knox of the real thing. In a world of increasing artificial intelligence, we have physical objects which anchor our knowledge of the planet. You might compare that then to GIS, which is the digital abstraction of reality. But I think as we move forward, Jack and I are talking about how do we blend these two things together? How do we take the benefits and opportunities provided by GIS and meld them with the incredible collections that we have in the museum? Museums are also the memory banks of our culture. If you didn't have museums, you wouldn't have the three-dimensional memories that anchor your memories. And this applies to historic culture and art museums and science museums. These are where our culture stores what it wants to preserve about our past. But more and more, we're getting concerned about the future. So museums are using the past to pivot toward the future. As a result, not only are we memory banks, but we're storytellers and we're future-oriented. It's much the same, again, with you watching when Jack spoke this morning about how there's an urgency about the present moment, that technology is advancing so dramatically, at the same time the challenges are racing. And it's a race between technology and challenge as we move into this century. And some time ago, I coined this phrase, the Dangermond gap. And it's really the gap between the huge advance of knowledge of our time and the public understanding of that knowledge. And I sit in a room like this of so many people who are so focused on this knowledge and interpreting the knowledge, and then think about how great it would be if everybody in San Diego or California or the United States or the world had access to the same amount of knowledge. How easy it would be to solve the world's problems if we could close the Dangermond gap. All right, so buckle up. This is going to be a pretty intense talk, so hold on to your seats. I'm going to show you one of our exhibits. This is called Deep Time. It's the history of life on Earth, starting with the formation of the planet, going all the way into the present and into the future. So we're actually incorporating the future in our exhibits now because the future is on us. The world's changing at a geologic scale, but a human pace right now. And by showing stories of successful activations and interventions, like we've seen here today in the presentation, we want to demonstrate for people that come to the museum that the world has a quite interesting past, a challenging present, but there are ways to solve for the future. The museum is also anchored by an incredible crew of scientists who are field explorers, there's discoverers, they're lab experts, they're analysts, they're communicators, they're scientific producers, and they travel the world searching for more objects for the collections. Field sites like the deserts of Utah, or the rainforests of the Amazon, or deeper into the rainforests of the Amazon, bottom of the ocean, deeper into the bottom of the ocean. Our purview is the globe. We go everywhere. And this map, generated by a query to GBIF, which is the Global Biodiversity Information Facility that is now available on the ArcGIS Living Atlas, we downloaded the 10.5 million items in our collections that are available through GBF. So this is only 7% of our collection that's plotted here, but you can see it pretty much is global in its distribution with only 10% plotted. One of our challenges is that much of our data is dark. It's not yet been digitized, it's not machine readable yet, but as it comes online, we'll have much more access to incredible data. As I went about my job as the museum director, it occurred to me that there are only a few large museums in the world. There's less than 100 what we consider large museums, more than 10 million specimens. And we decided to try and aggregate all of the collections in all of the museums because that represents what humanity knows and what humanity has preserved about the natural world. And we pulled together the work in 73 museums, and these are the largest museums in the world. You notice right away that they're mainly European and North American. There's a strong colonial footprint on where museums are located. They were invented in Europe and largely are in Europe and North America. And when we looked at these museums and aggregated their holdings, these museums hold 1.1 billion objects. And our goal is to create the One World collection, to be able to access all of the objects in all of the museums in the world, starting with the largest museums. I'll show you now GIS professionals around the world. And I know it's sort of a similar pattern, this strength in Europe and North America and scattering around the rest of the world. And the world is unevenly distributed in terms of its access to information, its access to museums, and to solve the problems of the future, we have to resolve this global north issue that surrounds us. Museum also has incredible iconic specimens. Here's the largest elephant ever known. Came from Angola in 1955. It was a 22,000-pound animal. It's been on display since 1959. It's been seen by more than 100 million people. So when a specimen comes to the museum, it gets real good public access. Here's a group of bison. The one on the right is the bull bison that was shot by William Hornaday in 1886 when the bison were almost totally extirpated from the northern Great Plains. This bison and this group of bison were on display at the museum from 1888 to 1957 before going back to Montana. And I will come back to this bison in a little bit. Here's a rhinoceros collected by Teddy Roosevelt in 1909. Here's a life-size megalodon shark based on a mako shark. And these are big, spectacular, historic objects that are jaw-dropping for the people visiting the museum. But the collections hold a host of things you might not think of as museum specimens, like this mosquito. We house the National Mosquito Collection. There are 2 million mosquitoes in our collection. And you might say, why do you keep mosquitoes? There's 3,600 species of mosquitoes. They're disease vectors. We work closely with the Army because one of the greatest causes of death for our armed forces are mosquito bites around the world. So we do a tremendous amount of work on mosquitoes and ticks and have large collections that will likely never see exhibition. We keep collections in a variety of ways. We skin and dry animals. These are preserved and they'll last for hundreds of years in this mode. We also pickle organisms. For organisms that we want to preserve their interior tissues, their parasites, their food base. And here are a shelf of pickled snakes. I'm sure looks quite delicious to you. We have 19 miles of pickled specimens. When I say it's nearly infinity, I'm saying it's nearly infinity. One of the great pleasures I have is I own the #1 key so I can access all these collections. And it is, for me, a museum person, it's awesome to travel the museum. Here's a pickled giant squid. Here's a pickled mountain gorilla about ready to get CAT scanned. We also preserve tissue frozen. And we do that because the breakthroughs in the genetic revolution, including things like the Human Genome Project, allow us to extract genomic-grade tissue from animals, and the best kind of genomic-grade tissue is frozen tissue. So we keep hundreds of thousands of frozen tissues on preserve. So we have these frozen ones we call popsicles, the pickled ones we call pickles, and the other ones are just dried. And then we have many collections. The collections go on. We have 442 named collections. The fossil collection, for instance, the National Herbarium, which has 5 million specimens of plants from around the world. The shell collection. The butterfly collection. The bird collection. And I note the woman in the foreground here is Roxy Laybourne. There's a book coming out about her next month called The Feather Detective. And she's the woman that invented forensic ornithology. You might wonder what forensic ornithology is, but you had a good presentation from the San Francisco airport here recently. What forensic ornithology is we get a tremendous number of bird strikes on planes, several thousand a year, and many of them cause fatalities as the planes crash. And Roxy Laybourne invented the ability to identify birds from their feathers or from their genetics in service of protecting air flight around the country. We presently host the FAA's Feather Identification Lab, and we get about, I think last year we had 12,000 samples flown to us for analysis. We also do similar kinds of work with the USDA, with NOAA, with NASA, with the USGS, with federal scientists embedded in the Smithsonian. Here's the mammal collection, and you'll note one particularly charismatic mammal on the right-hand side there. Mammals come in all sizes. Here's a gray whale that ran ashore on the beach at Whidbey Island in Washington State. And this animal was flensed and collected and brought into the National Whale Collection. Off-site storage, we have skeletons of all the great whales. There's 94 different kinds of whales, porpoises, and dolphins. This is the one place in the world you can see them all preserved and available for study. And of course, we have minerals, rocks, ores, rare earth elements, and this little rock. It's a little bit smaller than that, actually. This is the Hope Diamond, probably the most famous object in our collections. But minerals, there are 10,000 mineral species on this planet, 4,000 of which are formed in mediation with living organisms. And what I mean by that is your teeth are minerals, and you're a person, you're a primate, you're a mammal. Your body has made your teeth. Your body has catalyzed minerals. So the distinction between animal, vegetable, and mineral sort of fades away as we realize that our planet's mineral diversity is large because of the presence of life on our planet. These are thin sections of rocks. Rocks are made of minerals. The thin sections allow you to interrogate any rock. Think about all the rocks you've ever seen in your life and ascertain how old the rock is, what temperatures it formed at, what pressures it formed at. You can interrogate any rock and understand the history of the planet. If you interrogate all of the rocks, you can figure out how this planet came together, which is a big one of our questions I'll get to in a moment. We also monitor all the active volcanoes on the planet. There's 1,250 volcanoes on the planet that are erupting at some time in the last couple of thousand years, and a volcano never really sleeps. It's just some time before its eruptions. And we do this because many of the most dangerous volcanoes are located near high population centers. This is a safety kind of thing. This is sort of like Cal Fire 2.0, if you want to think about it that way. If Mount Lassen goes off, you'll have some wildfires to work with there. So sort of a surprise. This is done in partnership with the U.S. Geological Survey. And now I want to pivot, and I want to just embed you in biodiversity for a moment. You've probably heard the word biodiversity. It's not as commonly known as we wish it was. It's another word for nature. It's all the different kinds of living things that live on the planet. And we are the storehouse, the warehouse for all this biodiversity. These are what are called herbarium sheets. They're pressed, dried plants glued to paper. These things last for literally hundreds of years. This is how humanity preserves plants for time. There's over 450,000 kinds of plants. And as you can imagine, they're used for food, for medicine, for all sorts of things. But these are examples of the national herbarium. And we use different techniques to study plants. So for instance, we will sometimes take a leaf off one of these things, bleach out the chlorophyll, add a red dye, and create what are called cleared leaves. This allows us to look at the detailed interior vein pattern of these leaves and identify them and study how they move fluids around their tissues. Incredible things. There's about 5 million insect species on the planet, about 35,000 kinds of butterflies. Just a sampling here, huge collections of butterflies, and we're watching our insects slowly disappear. This is one of the various biodiversity crises we're seeing these days, is a decrease in insects and in particular butterflies. They start out as caterpillars, So lots of animals change their shape over time. They go from being one thing to the next. Caterpillars go through these various stages before they become actual butterflies. We also explore the oceans and find incredible things in places we never thought to look for before. These are specimens that were photographed about 700 feet below the surface of Monterey Bay. And these are organisms that you can't really sample particularly well, so we photographed them live. We'll capture them and put them in tanks and photograph them live. And the diversity of life just continues to grow and amaze us all. There's something like 35,000 kinds of crabs and shrimp. So everything you think of, maybe one or two things, there are literally thousands of different kinds. This is one of my favorites. We have an ant expert, and these are the faces of ants. There's 17,000 kinds of ants. There is a really nice heart-shaped ant in this mixture, too. There he goes, the heart, the Valentine's ant. But to me, they look like a bunch of thugs, basically. I was so charmed by these insect faces. But it's just to show you how many different kinds of ways we have of seeing the natural world. Often with fish, we'll, just like leaves, we'll clear them of their tissues, we'll bleach them out, and then we'll put dyes to study their vein pattern and their bone structure, making these incredibly different kind of ways of looking at fish. And again, with 35,000 kinds of fish in the world, very important for all sorts of biological reasons and for food and for ecosystem stability. It's really cool to know these fish. And what's really cool is that we can also X-ray them. That's another way to see inside fish. You can see several of these fish have contents that you can see, but it's also another way to actually understand the biology of fishes. And fishes, like butterflies, some of them have very different larval stages. So these are larval fishes. These are the kinds of things, we find these things like, what are they? The only way we can figure out what they are is actually doing the DNA on these fishes and then comparing them to the DNA of adult fishes. And these are the fishes that grow up to be tunas and swordfishes and perch and bass. But here in their juvenile stage, they are these spectacular little colorful goblins in the bottom of the sea. There's another 25 or 30,000 kinds of amphibians and reptiles. Snakes, lizards, frogs, turtles, alligators, and on it goes. You can see this whole thing. And when people talk about biodiversity, I just want to douse them in biodiversity to make them realize what a wonderful place planet Earth is and how much is, in fact, being challenged by the present growth of humanity on the planet. And of course, birds. Birds are incredible. 12,000 species of birds here just represented by their feathers. So all of these things are in the collections, and what we're trying to do now is to make them much more accessible. And to do that, we have to make them machine readable. So we are in the process of scanning and digitizing the collections. Here's a scanner that was processing 6,000 herbarium sheets a day. It took us 3 years to scan 5 million herbarium sheets, but they're all available on your iPhone now if you want them. Here's a scanner that we just installed that's scanning pollinator insects. And the little fly in the middle there is 3 millimeters long. So these are organisms that come in all sizes, and we're scanning about 1,500 of these a day to work our way through the collection of insects. Here we are scanning the large elephant in a partnership with National Geographic. It turns out that this animal came from Angola, and National Geographic is working with Angola in search of this race of elephants that may well have survived the Angola civil war that ended a couple decades ago. Now, one of the big breakthroughs in, where is my little jar, is the study of DNA that's floating in the water. And this is a jar of water that literally was collected off the east coast of Florida. And you can take a jar of water like this, scooped out of the bay, and strain out the fugitive DNA, the DNA of the organisms that were swimming in the water. And this jar of water has more than 1,000 different organisms represented by their DNA. So instead of sampling the organisms, we can simply take a scoop of water and see who's there. But the problem with that is that so many species exist in museum collections but have not yet been sampled for their DNA. So we've started a project now to sample our collections to make these samples light up. Basically remove the dark data from the collections by scanning and digitizing them. We're doing this in 2 test projects now. One is the project that is looking at the the exclusive economic zone, the 200 nautical miles that surrounds the US coastline. In those waters, we're aware of about 3,700 different species of fish. We presently have 87% of those fish in our collections, and we're about halfway through scanning those things. When we're done, we'll be able to literally take a scoop of water and tell you which fish are swimming in which section of water. In a similar project on the Indian River Lagoon, on the east side of Florida, that light blue section you see, we've collected and identified over 11,000 species of organisms, and we're doing the DNA project with those as well. We're going to build basically a DNA library that lets us rapidly assess change in biodiversity in all sorts of ecosystems, starting with marine ecosystems, then we'll go to freshwater ecosystems, then we'll go on to land. As we've been doing this, we've developed a concept with other museums called the extended specimen. The idea that a specimen in a museum collection is not very important unless it's associated with its primary information. And the information comes in a variety of ways. There's sort of the original stuff, the specimen number, where we collected it, those sorts of things. But there's also sort of this derived information, whether we scan its DNA, whether we put it into publications, whether we add it to large databases, or associated data. For instance, where other organisms of this species occur and show up on the GBIF or in other areas. So you have these three tiers of this extended collection which allow us to start to activate the knowledge that's in the collections in the museum. And I'll go back to this bison. Now, you saw him once before. This is bison. I call him the December 6th bison. He was shot on December 6, 1886, almost literally one of the last bison on the plains. This guy, William Hornaday, was bringing the animal back to display him in Washington, D.C., because the Smithsonian realized that the bison were literally going extinct. There was nothing to be done about it. Let's get a few to put on display so people could actually see bison. And the bison was mounted at the museum in 1888 and was on display until 1957. Millions of people saw bison for the first and only time. But Hornaday went on to continue to work on the bison. He did the taxidermy mounts of this bison. He started the American Bison Society. He worked with Teddy Roosevelt to think about how to conserve the remaining bison and start a bison range. And eventually they worked together to bring together all the information about bison and start the recovery of bison. And here is Hornaday's original 1889 map of the range of bison. So in around 1800, there was something like 44 million bison in North America. They stretched all the way to Virginia, down to Mexico, and up into Canada. By 1875, they were down to 8 million. By 1880, it was 1.5 million. And by 1886, when Hornaday collected that one bison, there were 700 bison left in North America. They almost went extinct. But fortunately for the mitigations that followed, and Hornaday continued to do this work, and here you see a knowledge graph showing two things. It shows Hornaday's map of the bison. It shows on the timeline the historical actions that happened with that specific specimen. The specimen was actually on the US $10 bill in 1901. And you'll see if you come to the museum next year a bronze statue of that very bison on the front steps of the museum. But that bison kicked off the recovery, and today, here's the distribution of bison in North America. There's about 500,000 bison alive in North America. And just last Wednesday, I wandered amongst a herd of them in South Dakota, and it was pretty amazing to sort of see a success story on such an iconic animal in North America. Now I'm going to zoom way out and take you back to the Earthrise shot that Jack showed you earlier today. This picture was taken on Christmas Eve, 1968. And Jack talked about how it catalyzed the conservation movement, kicked off Earth Day. But I'm going to show it to you from sort of a different point of view. This is the first time we get to see planet Earth, an 8,000-mile ball in space covered by an atmosphere, oceans, and continents. This planet formed with the solar system about 4.567 billion years old, and we don't know some very fundamental things about planet Earth right now. We don't know, for instance, where the ocean came from. We don't know where the continents came from. And we don't know when or how life started on planet Earth. Those are big questions we're pursuing. Our team was part of the OSIRIS-REx mission, which was a mission launched by NASA that went all the way 200 million miles out to an asteroid, grabbed a sample, came back, dropped the sample off. It landed in Utah in the desert. And the samples that we got 150 grams of samples. They came back to the museum where our guys analyzed them and discovered, to everyone's amazement, minerals very similar to the minerals you find in the evaporite lakes of Eastern California. There's a brine story in this asteroid that is 4.6 billion years old. And really what it implies is that there were places in the solar system that not only had these briny salts, but also had amino acids, and hydrated minerals, all the elements necessary for life. And this asteroid contains rocks that are older than the planet Earth. So it's a possibility that we might even find that Earth wasn't where life started. It might have started elsewhere in the solar system and be transported to the Earth. It's an interesting breakthrough. Here's the oldest piece of Earth we know. It's 4.3 billion years old. It's a single grain from Australia. And that leads me to thinking about our planet, the basement. And with so many of the maps we've seen today are all about where you are, the science of where. But the science of where, if you add deep time to the mixture, it gets very complicated indeed. And if you look at our planet and ask the simple question, how old are the rocks under your feet? We worked with Esri to create a baseline geologic map. Here are the oldest rocks of our continent. All these rocks are older than 500 million years old. Here are the rocks that are between 250 and 500 million years old. Here are the rocks that are between 66 and 250 million years old. And these are the rocks, if you want to find a dinosaur, go to where it's green. That's the dinosaur treasure map. And here are the younger rocks. So there's our continent. And if you look at our continent, one cool thing about our continent and this planet is the planet buries its dead. Layered rocks accumulate, they bury fossils, and we have a record of life on our planet that stretches back all the way to 3.5 billion years. This is an image by my friend Ray Troll, but it captures very well the fact that our planet is layered, full of rocks, full of fossils. These are fossil marine plankton. These are phytoplankton that are beautifully preserved, fossilized plankton that stretch back to about 70 or 80 million years. Here are forams. These are marine zooplankton, which are out floating around in the ocean right now. And these things are so cool because you can drill them up and they contain in them information about ancient climates. You can tell ancient temperatures. So they actually allow you to start building a climate curve for the history of the planet. Here are fossil leaves from one of our fossil sites I was digging last Monday. It's a site in North Dakota that has fossil plants from the age of the last dinosaurs. And you start to realize that the fossils give you as much information about ancient worlds as the living specimens give you about our living world. And of course, dinosaurs. These are incredible things. You would not even know that these existed if we didn't have museums. This is where you find dinosaurs. At the present moment, there are 1,000 known species of dinosaurs. There's a new one being described every 3 weeks. It's an amazing time in dinosaur discovery. There's also fossil mammals, the animals that lived once the dinosaurs went extinct. And what I want to do now is just take you on just a little bit of a wake-up call to GIS, which is that we always talk about the science of where, but if you go back in time, where starts to get confusing. So this is what it looks like now, but 66 million years ago, the planet kind of looked like this. And just watch North America. I'm going to take you back in time, 100 million years, 150 million years, 200 million years, 250 million years, 300 million years, 350, 400 million years. Got your eyes on North America? 450, 500, 540 million years. There you see North America lying on its side, covered by shallow seas in the southern hemisphere. There's almost no land in the northern hemisphere. And I ran the clock backwards. The continents move at about a ½ inch a year. That's a pretty good speed for a continent, actually, if you think about it. And we know, so that's one of the most predictable things about our planet, is we know where we're going to be, where North America is going to be in 200 million years. Because we know how fast we're going and we know which direction we're going. So that's the one thing you can predict about the planet is where North America is going to be in 200 million years. Let me run it forward. 500 million years, we had our first marine organisms. 450, we get our first little plants on land. They're about 1/4 of an inch tall. By 400, we get our first forests. By 350, we see our first coal forests, which give us the coal that drove the Industrial Revolution. By 300, we start to see the beginnings of the Pangea, the supercontinent, where all the continents come together. By 250, that continent was fully pulled together, and what was amazing is at this point in time, right at 252, we get a major extinction, which cleans the clocks of the planet. It was caused by huge eruptions that erupted through coal and oil fields, creating this massive carbon crisis, killed the oceans, and really reset the clocks on the planet. 200 million years, we see the first dinosaurs. 150 million years, we see the first flowering plants. 100 million years ago is what we call the global thermal maximum. This is a time when there was no polar ice. In fact, it was so warm that the mean annual temperature of the planet, which today is 15 degrees centigrade, at this point in time it was 35 degrees centigrade. Think about that. We're worried about 2 degrees warming now. Here's an example of temperature that was more like 15 or 20 degrees warming. 66 million years ago, a pretty unfortunate time. This little red dot over the edge of the Yucatan Peninsula is where the asteroid struck that caused the extinction of the dinosaurs and every animal bigger than a raccoon, about half the plants, killed the oceans. It was a horrific asteroid impact. The impact was about 6 miles in diameter, traveling 20 times the speed of a bullet. It created intense tsunamis, earthquakes. The debris raining down caused the sky to heat up to 350 degrees. There was enough dust to block the sun out for 6 to 8 months. It was, to our knowledge, the only example of a global instant catastrophe. It happened in a second, and it ruined the place for a long time. The survivors of that impact populated the world, and we're back to zero again. And one of the things that we thought about at the museum was it would be really important for us to know the climate history of our planet. So we set about a team of about 40 climatologists who came together and did a tremendous amount of work to publish a climate curve for the history of the planet, going back 485 million years. They did this by using the records from the ice cores. Our oldest ice core in Antarctica goes back at about 1 million years. They did it using the forams at the bottom of the ocean. Oldest of those goes back to about 200 million years, and did it using rocks and fossils on the continents going back to 485 million years. And what you see is a really interesting pattern. The blue bars, those 3 blue bars, one at 440, one at 250 to 350, and one now, are times when we have polar ice. The other times are times when we don't have polar ice, which is a really interesting discovery that for most of Earth history, we haven't had the polar ice that we have today. Now let me roll forward into this because obviously today we have polar ice. This is on the edge of the Greenland ice cap, which is 10,000 feet thick and about 100,000 years old. This is what it would have looked like in Boston or Chicago or Seattle 280,000 years ago. We had a massive ice sheet that covered it. And 280,000 is a pretty interesting number because that's about the year when our species, Homo sapiens, appeared on planet Earth. Our first Homo sapiens appeared in Africa. They moved out of Africa over time. But at this point in time, there were no humans in North America. There was a huge ice sheet. But the ice sheet melted away. It was gone by 220 million years ago. But it came back. And then it melted away again. And then it came back. And 20,000 years ago it was here. So this is not that long ago. 20,000 years ago it was only about 5 times the age of the pyramids. And then it went away again, leaving us with the planet we have now. And I'm going to show you an animation right now which shows you the movement of plants. Here's as the ice starts to move north. This is the ice starting 20,000 years ago going to the present. There's going to be yellow dots for oak trees and green dots for spruce trees. And you watch what's happening as the ice is melting away, 20,000, 18,000, 17,000, 15,000, 14,000, 10, 9, 8, 5, 4, 2, 1, today. And what you see is the evolution of our modern ecosystems, the boreal forest, the spruce-moose ecosystem, the broadleaf distribution of forests. And at this point in the talk, you're probably saying, why did this guy just give me a geology lecture, right? You're here to learn about Esri and GIS. The reason I did it is that we've entered a time now where, unexpectedly, the Earth's geologic changes are happening on a human time scale. Global scale things are happening on the time scale of our lifespans, and there's no better example than this. This is a curve that shows the carbon dioxide concentration in the atmosphere, plotted on the left, measured on Mauna Loa in Hawaii by a scientist from Scripps University named Charles Keeling. It's called the Keeling curve. He decided we needed to understand a baseline data for carbon dioxide in the atmosphere, and he started measuring it in 1957. He passed away a couple of years ago, and his son has continued the work, and the curve goes to today. And you'll note that in 1957, it was about 315 parts per million, and now there's 430. Now, I like this curve because it's exactly my life. My parents met in 1957. I was born in 1960. So this is a measure of my life. And the difference between when I was born and now is 36% increase in a greenhouse gas on planet Earth. That change has happened in the time it took to grow me from a little kid to the present state where you see me. So you're seeing a major change in the Earth's atmosphere in a child's lifespan. Here's the same curve over the last 10,000 years. 10,000 years, it pretty much gets us back to the beginning of human civilization. You can note between 10,000 years ago and quite recently, there was almost no variation in carbon dioxide at all. And then you can see it curve up. The Keeling curve now is looking quite vertical. If you add this is the comings and goings of the ice ages, which we went through. You can see that since 1960, the world has been quite a bit different than it ever was before in the last million years. So what we're seeing is a world that is changing on the scale of our lifespans. Geologic changes on the scale of our lifespans. And GIS is a really powerful tool for being able to interpret what's going on in the future. We look at map details. Here's Washington, D.C., showing potential areas of the National Mall that will be flooded by the year 2100, depending on if you get 1.5 or 2 meters of sea level rise by the end of the century. And these are very useful maps to predict future changes over time. And I find when I show these maps to people, they say, well, 2100, that doesn't matter to me. That's a long time from now. I don't care about the year 2100. It's 2025 right now. But this is the point that I really want to make, which is that time is deceptive. Here's a picture of me taken on Tuesday, last Tuesday, and that's a Triceratops fossil in the ground in North Dakota that we're excavating. I left it in the ground when I came out to do this talk. I'm flying back tomorrow morning to pull it out of the ground. You can see the horn sticking down. It's a complete skull of a Triceratops. So I haven't changed that much. 1973, I was looking at a Triceratops, and last Tuesday, I was looking at a Triceratops. I don't feel that old, and yet the atmosphere has changed 36% in the time of my short life. Or it's not that short, or it is, but this is the point, is that these things are happening in our lifespan. It's not something for future generations. And it really made me think about what matters to me, and I would say what matters to you, and really what matters to us all most probably is our family. Our parents and our kids, our grandparents and our grandkids. Those 5 generations that map the people that we care about. We care about what happened to them in the past. We care about what happens to them in the future. So I came up with this idea called the time shadow, which is really just that time from the birth of your grandparents to the death of your grandchildren. That span. And you should think about yourself in that time frame, what matters to you? How much do you care about how life is going to be like in the year 2100? And it turns out it's a problem. Here's my time shadow. This is my grandfather, born in 1879. He was 21 years old when the century turned in 1900. I knew him for 3 years when I was a kid. Here's my mom, who grew up on a ranch in Wyoming. Here she is in 1937, grew up on a calf. Here's my sister and I. We were born in the 60s. Here are my sister's kids, born in 2012. These kids will in all likelihood see the year 2100. They'll be 88 years old. They'll be citizens of the 22nd century. And their kids will probably pass away sometime around 2140. So the future is here now. It's upon us. And one way to visualize this is to look at human population as a measure of the urgency of the now, of the moment. And the population of this planet is a remarkable thing to watch. I mean, for 20,000 years, it didn't change hardly at all. We didn't cross 1 billion people until the year 1800. But when you plot your family on this population curve, you realize that the growth of population that we all sort of accept that we're growing has actually happened in the span of my particular time shadow. You can map your own families onto this curve and see how it goes, but really, we live in a time of incredible urgency in so many different ways. And as Jack so eloquently put it, things are developing really rapidly, and they're most interesting, but there are also challenges chasing them forward. And the way I look at this is I'm a museum guy. I'm going to solve problems with museums. Museums are my tool. There are amazing numbers of museums. Here's a map that we did for this talk that shows there's almost 1,000 museums in North America of natural history. 1,000 little versions of these things where people gather information, share the information with people. And I do think that museums are a great place to approach the challenge of the 21st century. But I also really think that this audience, I've never seen in one place in my life so many talented, smart people who are understanding data and mapping it spatially, thinking about the future, being planners. And my appeal to you is that you use the skill set you have, use GIS as a toolkit, and perhaps you can be some major part of how we negotiate the century in front of us. And I was in London a couple of weeks ago and saw a presentation by Dave Attenborough, who's 99 years old now. And he pointed out, he said, the problems of the 21st century will be solved by people who are alive today. So it's an honor to speak to you, and I challenge you to join me in an attempt to help us close the Dangermond gap and share the knowledge that we're gathering for the benefit of people of the future. Thank you very much.
Thank you, man. Extraordinary.
Thanks.
Don't you want to say something else?
I tossed out a big challenge there.
Yeah, I did. Did you enjoy this?
It is, 1,000 samples.
I see them. Look, I've come to know Kurt pretty well. We've become friends.
Yeah.
Science of where, science of when.
Exactly.
Is that the fundamental discussion? And he's grabbed my heart.
I'll give it back to you one day, don't worry.
Yeah.
No, I think we're of one mind, it does feel. And I think the molding of museums and GIS is such a natural thing.
It is.
And it's a powerful thing to put these two amazing resources together.
I have a ton of questions, but we'll probably do it later.
Yeah.
Brian, have you ever had your kids to the Smithsonian?
We've been there, but I don't think I've had the backstage tour that you've had.
Like in the basement?
Yes, I saw a picture of that interesting mammal.
That's right, the charismatic mammal.
The charismatic mammal. So one thing that really jumped out for me, Kirk, was amongst all of that really thought-provoking talk, there was one little thing with a knowledge graph, which to me was this fascinating intersection of our communities, right? Trying to understand where everything came from originally, where it was discovered in our lifetime, and where it sits today in your museums. And I think that's going to be a really exciting journey to follow along with you.
Yeah, well, our whole team at the museum now is looking at how we can work with GIS to really amplify our impact, because I've been coming to these presentations for some time now, and it's like, this is a natural thing. We have this incredible untapped pool of dark data that's relevant to the future of the planet, and somebody's got a really cool toolkit.
And you're scaling up.
Yeah, exactly.
Yes.
I mean, there's so many ways this could go. One of the things is location, and you're digitizing everything, you're putting location on them. This is going to open up not only your museum, but, well, museums around the world to integrate everything everywhere, to use a phrase.
And every when.
Every when.
Every when, yeah. When, where, all of it. Look, you challenged the people here in the audience. I'd like you to bring it home and be more specific. What would you like them to do?
Well, as I showed that map of 1,000 North American museums, so no matter where you live, there's a museum nearby you that's probably underfunded, understaffed, hasn't really thought about this. And I do think that museums, because they are unique places, I mean, you think about all the things in your town, there's lots of businesses,
Right.
there's lots of places going about stuff, but there's very few organizations that are dedicated toward preserving what has happened and therefore providing the feedstock for what will happen.
Yes.
And it does seem like the melding of people in this room with their home communities. We're working a lot, for instance, with tribal museums right now, the concept of how do we connect the collections that we have from Native Americans with the tribes and the tribal museums. So there's lots of ways you can imagine the large mother museum supporting the small museums, but obviously everyone in this room comes from somewhere in the world where museums are doing that same function in their areas. And of course, I'm a museum guy, so I have museum sunglasses on.
Sure.
I only see things through museum lens, but I do feel that they're unique opportunities, and most people think of them as buildings full of exhibits. They don't realize that they are future-facing organizations that can dovetail really well with other organizations that think about the future in a deep time or a deep future kind of way.
Well, one of the things that you have in mind, you don't mind if I share it, is to
Please.
digitize the whole museum and provide location about every object, and then provide virtual, like we saw just before lunch, virtual reality tours from any place on the planet to your museum by kids who want to learn, apply AI to it. You can see where that's going.
Yeah, and I think then too, like this whole idea of the knowledge graphs and how you take all that data and map it on to time and space. I mean, it's a pretty open field right now.
Integrating everything everywhere.
Yeah.
The other interesting concept is what you're doing in eDNA.
Yeah.
And so I see location as a way to integrate everything, as everybody in the audience does. But there's also this notion of looking at species and their DNA and connecting life through time and space.
Yeah, it's such a breakthrough. I mean, the fact that this glass of water has 1,000 species in it, and you could sample this in San Diego Harbor every Tuesday for the rest of your life and see how things change over time. It gives us real intelligence on how the world is changing.
Don't you agree that science is the foundation of everything?
All it means is to know. It's knowledge, it's how do you get knowledge and how do we share it? I just love the idea of closing the Dangermond gap, because we've got all the parts, now we just got to close the gap. And that's how we communicate with the broader public. Because everyone in this room is knowledgeable on this topic. It's a room full of experts. It's 15,000 experts in one room. What an amazing concept. But across the street, you could ask a question and you might not find that same level of knowledge about maps or GIS, whatever. People are afraid of science, they're afraid of math, and I think that it's a big challenge for us to be able to provide tools that allow us to educate the public in an actionable way on the time scale that we have, which is short.
How many of you are interested in this topic?
There we go. Good.
Don't you need volunteers?
Yeah, was that at least 1,000 volunteers right there?
Okay. Actually, seriously, there is a major effort at the museum, but also I like your idea of adopt a museum locally and start copying the patterns that you're going to build on this digital twin.
And if we build a toolkit that works for us, it could work for everybody too. That's the nice thing about it. It becomes a network of connected museums. And I can tell you right now, the large museums of the world are thinking about how to do this. And we start with the big ones, which have the huge collections, but then you cover all the small ones, which end up being more and more point connectors to small communities.
Thank you for being who you are.
Hey,
Thank you for coming off the dig. The T-Rex is up there waiting for you. So
it is. I'll go dig it out tomorrow.
Thank you again, Kirk.
Thanks, Jack.
Ladies and gentlemen,
Thanks,
Kirk
Brian.
Johnson.
Good to see you.